Setup for this lab, the conditions for static equilibrium. I want to show you what I'm going to try to do here. Right now, notice how that reads 0 newtons, but I'm going to do this. I'm going to pull on it and then let it stop. Notice it's not reading that anymore. I believe that this is going to be one of the biggest issues with this lab. So how far can we possibly be off? I bet a couple tenths of a newton easily. Nope, still a little off. So I'm going to do that with all of them and hope that that helps out with the error. So here's my setup. I've got a meter stick with 4 forces on it. Yes, that's my foot because I'm almost all the way up to the ceiling trying to get a video of this for you. Now, it's in static equilibrium, which means it's not moving, it's not rotating. And so we're going to actually work out the X and Y components, all of that stuff here in a second to prove it to you. We already saw that possibly these forces are probably not, they're not as perfectly accurate, a lot of friction and other things. So we're going to go through and record each one of these and then go onto the computer and do some work. So here's a quick sketch of what we have here. So let's go ahead and get some amounts. So this one reads 1.246. So this is 1.6 newtons. We're going to get the angles here in a bit. This one is, there we go, 4.1. That's really hard to do. 4.1 newtons. Down here we have 1.2 and 3.6. 1.2, 3.6. Other things to make this terrible, as for accuracy, I thought I put these underneath. You couldn't read them at all, so now we're just going to kind of have to guess what direction that is. This is the upper left, and that's somewhere around, what is that, 106 degrees. Not that we're anywhere that accurate. We'll call it 106. What the heck? This one down here, we're going to call 260. Show me setting it up one time. It's so exciting. Got to try to find the hole there. There it is. I'm making 0 to the right, just like the calculator likes. And that reads around 72. We could get really good and call it 72.5 because it's, again, no way that we're that accurate. Done this over the years, but here we go. So there's 80, somewhere like that. 270, which is what I wanted it to be. We'll call it 270. So there it is. That keeps the bar in static equilibrium. Now it's time for us to go and try to do this math-wise. I don't have a lot of time here, but let's see what I can do here. We'll try to get some of this analysis done. Now, I made this 106 degrees, which means for me, this is 0 degrees. Okay, this is 90 degrees, 180, and 270. Why? Because I want their absolute values. I don't want to have to say, oh, that one's negative, that one's positive. And I'll show you how this works out in the calculator. So we'll start with this first one over here on the upper left. And I'm going to use sine for the y direction and cosine for the x direction. Make sure you can see this. Okay, so for the upper left one, we're going to do 1 point. Let me make sure that I'm in, should be 0.5. Good. Okay, so 1.6 sine of 106 gives me 1.538. So the Fy, and oh, actually, let's do this. Yeah, that's fine. Okay, so Fy is 1.538. I know it's not that good, but we're still going to do this. So, and then 1.6 cosine of 106, and that's negative 0.441 newtons. Down here at the bottom, we have 4.1 cosine of 260, which gives me negative 0.712. I mean, those blah, blah, blah. And Fy equals, that's cosine, okay, 4.1 sine 260, and that's negative 4.048. I probably shouldn't be doing that many decimals, whatever. So over here, okay, we'll do this one up here. 3.6 cosine of 72 equals, was that 1.11 newtons? That's Fx. Fy equals 3.6 sine of 72 equals 3.42 newtons. 1.2 cosine of 270, that should give me 0 because it's just pulling down, and Fy would be 1.2 newtons. Okay. Now let me go ahead and transfer this and let's put it into a table. So we have our forces, and we're going to have our X forces and our Y forces, and then we're going to add them together. Okay, so I have X forces. I have negative 0.441 and Fy. Okay, so we have negative 0.441, negative 0.712, 1.11, and 0. In the Y direction, I have 1.54. I'm just going to get rid of that. Negative 0.405, 3.42, and 1.2. Let's add those together. Move them to where you can see them better. I apologize. So let's go ahead and add these together. Negative 0.441 minus 0.712 plus 1.11 gives me negative 0.043 newtons. Wow, that's really good actually. And these are our nets or totals, right? X direction, Y direction. In the Y direction, 1.54 minus 4.05 plus 3.42 plus 1.2 gives me, ooh, that's not good at all. Wow, that's a lot higher than I was hoping for. Let me just double check this on my computer, make sure that I got those. I'll put them in my computer. No, I did something wrong. So I get 1.54, got it, 4.05, 3.42, oh, that's a negative, that's the problem. That's the negative, okay, sorry, duh. All right, so what does that do for me? My calculator, my computer says that that goes to 0.0405, okay? Now let's look at those two numbers. Those two numbers are, sorry, keep my eye on the clock here. So those two numbers are extraordinarily close to 0. And I would say that we did a pretty darn good job there in the lab. So the net forces in the X direction equal basically close to 0, and the X direction, the Y direction forces equal basically 0. That's pretty cool. Now the next thing is it's not spinning, so we have to figure out the torques. All right, so we need to find the net torque. But in order to find the net torque, we do need to know we need to pick a pivot point. Let's use 0.5, the center of the bar, 0.5 meters as pivot. All right, and then we need to find the torques for each of these. All right, so for the first one, looks like we're gonna use just the Y forces, right? Because those are the ones that are gonna torque. If this is our pivot, there's our pivot. Notice this is gonna turn this direction, which is a negative torque. This is going to be a positive torque. This one's going to be a positive torque and a negative torque. So I wish I had a pen here and you could see this easier. I don't have a pen on me right now. Sorry. So our torques, we're going to get positive torque equals our distance from the pivot. This is 50 centimeters. So our distance here is going to be 0.2 times our Y force, 4.048, and that's going to give me 4.048 times 0.2. That gives me 0.81 Newton meters. This one up here is going to be, making sure you can see what I'm doing here. So my distance to this one is going to be 0.4, all right, 5.4 times that gives me a negative torque I'm just going to use, so that calculates out to be negative 0.615 Newton meters. I got this on my computer, so that's why I'm doing this faster. Over here, I've got my y, and this is going to be times. That's only 10, or 0.1 meters. That one, let me see the 3.6, that gives me a torque of 0.342, whatever, Newton meters, and that's a positive torque, negative torque. This one's a negative torque. It's going to be 1.2 times 0.4, which gives me negative 0.72 Newton meters. So those are our torques. I got to go back to class here in a second. So that net torque works out to be actually I can just give it to you. The net torque equals negative 0.185, which is unfortunately quite a bit lower than each of those. So it's pretty close to zero. Okay, we'll come back and talk about that in a bit. Only one more thing we have to do here. We have proved basically that if an object is in static equilibrium, the net force is equal zero, and we found out that the net torque equals zero. But that's not the condition, is it? Well, you may not know this. The condition for static equilibrium is that the net torque is zero about any pivot. So now we have to pick a different pivot. We've already picked the middle to be the pivot. Let's pick the left. Let's say it's at 0, okay? So I'm going to take these numbers and transfer them. So we have, we're going to do, here's the pivot. I'm going to give the distances and the forces. You can't see it, but I'm going to write them down here. So at this one, it's going to be 0.1 meter and 1.538 newtons. This is going to be 0.3 meters, and the y component is 4.048 newtons at 60, so that's 0.6 meters. The y component, 3.42 newtons, and here at 0.9 meters, that's 1.2 newtons. Let me just double check I've got them all. There we go. Okay, I think that's correct. So now, let's go ahead and find the torques. Now in this case, this would be a positive torque, negative torque. So this would be negative torque, positive torque, positive torque. So let's get those. So 0.1 times that will equal a positive 0.1538 newtons. This would be 0.6 times 3.42, and that gives me a positive 2.052 Newton meters. This one down here, 0.3 times 4.048 gives me negative 1.214. I'm just going to take all the numbers. I know sig figs is kind of stupid. And 1.2 times 0.9 gives me a negative 1.08 Newton meters. Let's add all those up. So I get 0.1538 plus 2.052 minus 1.2144 minus 1.08 gives me, wow, that's a small number. Which, compared to those, that's relatively small. So I'm going to say it worked out to where our net torque equals approximately 0. And then when we did it from 0.5, pretty close to 0 as well. Now again, remembering that what we did back there, very little of that was very, very precise, right? You know, we could have been off by several degrees on the direction. I figure the forces were off by at least 0.2 newtons. So all of this is very squishy and so forth. So now we have come to, I'll use this piece of paper right here, and let's write our conditions for static equilibrium. Conditions for static equilibrium. I would like to do this on the computer, but my computer's not doing a screen capture very well right now. Conditions for static equilibrium. 1, the sum of all forces equals 0. That means that the sum of all forces in the x direction equals 0, the sum of all forces in the y direction equals 0, and I guess I should do this, the sum of all forces in the z direction equals 0. Then 2, the net torque equals 0 about any pivot. It doesn't matter what pivot you choose, the net torque will equal 0. With those two conditions, net forces equal 0, net torques equal 0 about any pivot, you can solve any static equilibrium problem.